All right, we're very happy this week to have Nate Harman speaking, and he's going to tell us about the representation theory of VIC-Modules.
Great, thanks. Yeah, so I want to talk about some representation theoretic aspects of VIC-Modules, or sort of, you know, my current understanding of it. I should say I haven't really been thinking about representation stability much this year. I'm at the IAS for like a special year in geometric and modular representation theory, and so I've been sort of focusing on projects related to that stuff. But it was kind of fun to force myself to give this talk and you know, go back to thinking about things that I was thinking about like about a year ago. And kind of it's got me excited again about some of these results that I'll tell you about, and some sort of work that was left in progress when I abandoned it to focus on IAS stuff. But yeah, so I'd like to give sort of an overview of this theory. All right, so that's all right. All right, so before I start talking about VIC-Modules, well, let me just remind everyone about FI-Modules. And kind of the point is, I want to treat the theory of FI-Modules as sort of like the gold standard for results in representation stability, right? So in particular, I'm going to focus on kind of three main results from Churchill and Berg-Farb about kind of structural results about FI-Modules that to me really represent sort of some of the main aspects of the theory. So the first one is Noetherianity. So the Noetherian property is that if you have a finitely generated FI-module and a submodule inside it, then the submodule is also finitely generated. Right, so, you know, this might not seem particularly kind of representation theoretic, but this result is sort of very important both for kind of applications, like we use this a lot in sort of showing that representation stability appears in the wild, but also for really kind of getting a hold on the internal structure of finitely generated FI-modules.
But Nate, this fact is not from Churchill and Berg-Farb, it's from Churchill and Berg-Farb and Oddball, I feel the need to point out.
So yes, although I do have characteristic 0 here.
Oh, it does say that. Sorry. Okay. Continue to throw my student under the bus.
Yeah. So today I'm going to mostly focus on characteristic 0. Of course, the modular theory is also super interesting, but there's, I think figuring out what happens in characteristic 0 is sort of the first step for doing anything in positive characteristic as well, or even more so integrally. All right, so we have Noetherianity. We have control over dimension growth, right? So if I have an FI module and it's finitely generated, then I think of it as a sequence of representations, and the dimensions of these representations is eventually polynomial. And I mean, so this can be generalized. It's also true that the character values, other character values, are also polynomial in a sense. But in some sense, I want to say this is one of the, like, in some sense, kind of coarse things we get out of representation stability. But it's also maybe one of the things that we actually care about the most, right? For a lot of these applications, understanding like how fast the dimensions of cohomology or homology are growing is maybe actually more important than like understanding the internal structure of them. So some sort of control over dimension growth will be an important part of this theory. And then finally, multiplicity stability, which really I think sort of is informally what people who may be outside of this seminar think representation stability is really about. So this is saying that we have an FI module that's it gives us a sequence of representations of symmetric groups, that the decomposition into irreducibles sort of doesn't depend on n past some point, up to some funny relabeling we do, where we take a partition and we kind of keep making the first row longer and longer. So hopefully this is kind of familiar to everyone. And so I want to say these are sort of what to me, I think of as being kind of the gold standard representation theoretic results about, modules over some category like this. And kind of depending on the context, we might have to relax some of these things or modify them in certain ways, depending on both changing FI to some more complicated category or changing the ring that we're taking our representations over. But kind of everything should, often we want these to hold, and then we see what does hold. We see how close we can get to these things. All right, so that's the thing to have in mind, kind of going forward. All right, so now let's talk about VIC. All right, so first of all, what is VIC? So if I have a ring R, and I typically, I'm gonna assume R is a commutative ring. Often even it'll be a finite ring. But so VIC-R is our analog of FI. And what it is we take finite rank free R modules and split injections between them. So these are linear injections, R linear injections, and by split I mean that we choose a choice of complement to the image. So I include one free R module into another in such a way that there is a complement, and then I choose such a complement. Another way to think about these, instead of choosing this complement, is it's the same as choosing a surjection the other direction, such that the injection and the surjection are composed to the identity on the smaller space. And that's often a useful way to think about it. All right. So that's VIC. It's our GL analog of FI. And a VIC module, or VIC-R module, over some ring K is just going to be a functor from this category VIC-R to modules over K. And for today, I'm going to assume that K is an algebraically closed field of characteristic 0. So characteristic 0 is going to be crucial. Algebraically closed, I know some of you people don't like doing that, but it's a simplifying assumption for representation theory, and for some of the results, it's a nice simplification. It's something that we want to assume. But of course, you can always, if you get weaker results over non-algebraically closed fields that you can obtain by base changing. So it's algebraically closed is the more mild thing to remove. But all right. So concretely, just like for FI modules, we have this definition that's sort of in terms of functors from some category into vector spaces or modules. But in terms of representation theory, that's not always like the nicest way to think about it. And so kind of a better way to think about it for my purposes is we think of it as a sequence of representations, V1, V2, V3, and so on, where Vn is a representation of GLNR over our field K. And the maps, we have a map from Vn to Vn plus 1, which is a map of representations for kind of GLN acting on Vn and GLN acting on Vn plus 1 under like the standard way of embedding GLN into GLN plus 1, right? In sort of upper left block matrices. Right, so we have a sequence of representations with these maps from one to the next. And then the key sort of VIC property is that if I take GLN and I put it inside, I map it into, if I take Vn and I map it into Vm for some m much larger, that then this complementary copy of GLM minus n, so this is now kind of lower right block matrices, you have this complementary copy of GLM minus n that has to act invariantly on your image. Right, so this is, if you've gotten into the weeds of working with FI modules as a sequence of representations, this should be very familiar. This is kind of the same setup, but we just have, GLN instead of SN. All right, so this is, these are VIC modules. And so now let me, I'm gonna kind of give an overview of like some known results about VIC modules. Before I do so, I wanna not offend anyone, especially in this audience. So I'm focusing just on aspects of the theory that are sort of representation theoretic in nature. So of course, there's been a lot of work kind of applying these ideas to other areas and work kind of focusing on other aspects of the theory, sort of more homological results. And I'm not going to cover everything, so don't be offended if I don't cover your favorite result in this this overview I'm about to give. But okay, so here's kind of a history of kind of results in about VIC modules, kind of, or at least the representation theoretic ones. All right, so first we have this paper of Putman and Sam in 2014, where they defined VIC. So that of course was an important step in the history, right? And then they proved, well, a number of things, but they proved kind of two results that are kind of crucial. So the first one is that
I think the French polynomial people are mad at us for not acting like they invented the definition of VIC.
So
I don't know the history.
my
but
impression is that they don't look at VIC. They look at something like all linear maps between R modules is more the type of thing that they look at.
They definitely have also looked at VIC though in those papers.
Well, in any case, certainly, I mean, there's some aspect of, they speak a different language, and it's not French that I'm talking about. But yeah, so there is this French school as well. But anyway, okay, so we have VIC R modules, and we can argue about who defined them. But okay, so one of the like key results early on is that if we have a finite ring, then VIC modules are Noetherian. So again, we have this property that if you have a finitely generated VIC module, and you have a submodule inside of it, then the submodule is also finitely generated. Great, that is a bare minimum thing we need to work with. But of course, the problem with that being a bare minimum thing we need to work on is that it's false for infinite rings. So Putnam and Sam show additionally that if you're not a finite ring, then this is false. There is a finitely generated VIC module that has a non-finitely generated submodule. So that's going to be a problem, but great. That's a good thing to know. All right, the next step in this history is there's this work of Gahn and Waterland, where they work over a finite field. And so they look at VIC FQ modules, again in characteristic 0. And they show a polynomiality result for the dimensions, but it's kind of a funny polynomiality. It's not polynomial in n anymore. It's polynomial in q to the n. So this is like sort of a modified version of polynomiality, but still this is some control over how fast the dimensions are growing in a VIC module. And then additionally, they show that over an algebraically closed field of characteristic 0, there's a nice labeling of the irreducible representations. They're now in terms of kind of lists of partitions, kind of functions from some set of cuspidal representations into partitions, satisfying some combinatorial properties, that under this kind of natural labeling that we have, we see multiplicity stability. So it again amounts to, you have some list of partitions, one of them is a distinguished one, and we just keep adding a box to the first row of that distinguished partition in our list. So that's nice. So and maybe here I want to pause for a second and say here, the fact that we have this nice labeling and can do this, this is where kind of the fact that we have an algebraically closed field is coming in, or this is one place where it's coming in. So while for symmetric groups, it is true that every irreducible representation of symmetric groups is defined over the rational numbers, right? So that means that there's sort of no difference between working over the rational numbers or the complex numbers or any other field of characteristic 0. Whereas for GLN-FQ, that's just not true anymore. You have to have certain roots of unity. So and the number of roots of unity and things that you need grows with n. So there's no finite extension of Q that has all the representations of all GLN-FQs defined over it. So we might as well just go to the algebraic closure. So that's my aside about taking algebraically closed fields. All right, so what's up next?
But Nate, can I ask?
Yeah.
This is a little bit of a naive question. I don't really remember my complex representation theory of GL and FQ, but are these, I thought that representation theory, the irreducible representations were more wild. Are we saying that only some of the representations of GL and FQ are allowed, the ones that correspond to partitions, or like what's? No,
these are, for GL and FQ in the representation area is not that bad.
Oh, it's not that bad, okay.
So I mean
over C, every finite group has good representation theory, right?
This is true, but that's a little bit of an oversimplified statement, and we'll see in a minute.
But it's not literally in bijection with partitions of n, right?
So it's no. So it's
that's what I'm not understanding.
These are functions from cuspidal representations, which is some set of special representations, to partitions, and the functions have to have sort of total weight n for some notion of weight. So the partitions themselves are coming in terms of kind of parabolic induction from block Levy factors, but the cuspidal ones are coming from these are ones that kind of don't occur in any parabolic induction. They're coming from kind of the following. So if I look at GLN-FQ, so sitting inside of GLN-FQ is a copy of GL1 FQ to the N. And this is something that like you see in GLN, but not in any smaller ones, right? You start seeing, you know, roots of your characteristic polynomials living in the nth degree extension. And so roughly how you get Cusseler representations is you take a character of GL1 FQ to the N and you induce it up to the full GLN FQ. That doesn't work. That's not actually how you get the irreducibles. You have to do a modified version of induction, Delian-Lustig induction. But essentially what I described, where you just induce up a character from GL1 FQ to the N, that gives you the right answer up to twisting by a Steinberg representation. So it's not that far off. But yeah, so these Cusseler representations are coming from kind of these tori that are living over field extensions. And then you kind of put them together and do parabolic induction to get these partitions. But so it's a nice description. We know it completely for GLN-FQ. We have the character table, everything you could want in characteristic 0. Cool. All right, let me keep going. So next result I want to about is a result of our very own Peter Potts, who so he looked at VIC-Q modules, which are pointwise rational or pointwise algebraic. So meaning that they sort of come from an algebraic representation of the algebraic group. And so we saw that if you have an infinite ring, that Noetherianity just doesn't hold. But what he does is he shows that if we look at this restricted class of representations, these ones where all the the pointwise representations that are occurring are satisfy this rationality condition, then Noetherianity holds. So this kind of means that, like, considering all VIC modules is maybe not the right thing to do when we're in a setting where our ring is infinite. But if we have some smaller class, we can get a nicer theory. And he really proves kind of this entire, what I was calling this gold standard. So he proves this Noetherianity result. You have polynomiality of dimensions. They're finitely generated and pointwise rational in this sense. Then your dimensions are eventually polynomial. And moreover, we get multiplicity stability. So there's a natural way of indexing rational representations of GLN-Q in terms of sort of pairs of partitions. And while for any fixed pair of partitions, it makes sense provided n is large enough to sort of be able to separate those two partitions. But it's sort of a nice kind of stable labeling in terms of pairs of partitions. And Peter shows that that in this we have a nice multiplicity stability statement.
And the definition of this multiplicity stability was already due to Tom and Benson in their very first paper back when. That's
right. I mean, so certainly Tom and Benson kind of predicted a lot of the theory of representation stability in that initial paper before a lot of this machinery was built up. So yes, absolutely, this notion of multiplicity stability for general linear groups over Q was noted and predicted by Tom Church and Benson Farm. Great. So this, this is of course a very nice result. And one thing that I think really kind of one of the big takeaways that I took from this was that this idea of kind of restricting to a nicer class of representations when we have an infinite ring is sort of, well, A, necessary because we have this kind of total failure of things that Andy and Stephen showed if we don't assume something like that. But then B, it actually can give you some really nice results, like this this result. So kind of with that in mind, that motivates some work I did a couple years ago. So I looked at pointwise finite dimensional VIC Z-modules. So pointwise finite dimensional is what it sounds like. Each of the VNs in my sequence of representations is going to be finite dimensional. And the results in that work were as follows. So again, under this pointwise finite dimensionality, what, Jordan? Under this pointwise finite dimensionality condition, we have a theory entity, so we can pass finite generation to submodules.
Sorry, Nate, what are you assuming about your field?
This is again characteristic 0. Well, for Noetherianity, characteristic 0 is enough. I mean, I think in that paper I was assuming I was working over the complex numbers. Ultimately, it doesn't. Well, no, probably algebraically closed characteristic 0 is what I'll need for the full strength of this. But if you relax algebraically closed, like morally, most of it goes through. You have to modify the statements. All right, dimension growth. Again, not so bad. So it's no longer a polynomial, and it's not, kind of polynomial in a single q to the n. But the Hilbert series is a rational function in T. And this rational function growth is something that we've seen in kind of other parts of representation stability. Certainly not, not the least of which being things like FS op modules and things like that. So this is not, I didn't come up with this idea, and in fact, like more or less, this follows from some work that Andrew Snowden and Stephen Sam did. Well, building on stuff I did here, and then finally, the kind of main result in that work was the following superrigidity theorem. So if I have a pointwise finite dimensional VIC Z module, then okay, so some weird stuff can happen in kind of low degrees. So up to torsion though, if we work sort of in the generic category, then V admits a finite filtration by VIC submodules, and then the successive quotients are all of the form AN tensor Fn, where the A's are a restriction of a pointwise rational VICQ module, so the stuff that Peter Pat studied, and the F's are coming from a VIC Z mod MZ module for some n, right? So they factor through a finite quotient. So A stands for algebraic, F stands for finite. So this was the sort of final, the punchline of that theory. All right. So, and probably many of you heard me talk about this 2 years ago. Okay, so this is kind of the end of the history part of this talk. And so now I want to say, here I want to give a list of things I was sort of dissatisfied with about the theory of VIC modules, some of which I'm still dissatisfied with, but kind of things that I didn't understand or thought could be better understood about this. So first of all, I want to understand stability for finite rings that are not fields. So we have this this multiplicity stability statement, but it only works for finite fields. And kind of we don't think that you know, finite fields should be that different from finite rings. But you know, we don't have any we didn't have any kind of hold over what happens for.
But Nate, isn't it true that because I had a student who's we realized that we didn't really understand this at all, but like the representation theory of like GLN Z mod P to the KZ is like way harder, right? So why do you say it shouldn't be any different?
Yeah, I'm gonna say that in a second. Yeah, an important thing is that we don't even know the character tables for GLN of Z mod P to the KZ. Like,
yeah, that's what I was. That's I screwed over my own student by not realizing that that was hard. I was like, oh yeah, go look this up, and then it doesn't exist.
Yeah, it's way harder and open. Yeah, this is this thing where like sometimes we think like, oh, you know, this is a question that is like about representations of finite groups in characteristic zero. Like, surely everything is known, but no, that's not the case. So this is what I was alluding to earlier when Peter said, oh, things are nice because you have a finite group in characteristic zero. That's not, you know, that. Like, yes, we know things behave well in some respect. It doesn't mean we know everything. Yeah, so that's exactly right, Jordan. So part of what makes this so difficult is that we don't even have a natural labeling of the irreducible representations of GLNR for rings that are not fields. That's the problem. But all right, what else has bothered me? So I want to what I call decoupling the primes, or decoupling the prime contributions. So this super rigidity statement, so I'm working over Z. So it lets me kind of separate out this infinite place, kind of the representations that are coming from GLN-R, GLN-C, this algebraic part. But then I have all the finite parts kind of just clumped together. And morally, we should expect to be able to decouple the different primes. So morally, we should expect a sort of adelic factorization of a VIC module. And at the time I wrote that paper, I kind of had some trick essentially for pulling out the algebraic part, but then all the finite things got kind of just grouped together. And I at the time I just moved on, but that shouldn't be the case. You should be able to, separate the factor coming from 2 and the factor coming from 3, and have them act separately. All right. So another thing is other number rings. So O will be, the ring of integers in some number field, and we think that this, looking at GLN-O versus GLN-Z, we kind of expect something should hold. If we know we have the super rigidity result for Z, we should get it for O as well. And morally, that seems like it should be true. There's a lot of things that screw up if you just try and run the argument that I had for anything else. So for one thing, you have kind of multiple infinite places now. You have more than one way to embed your ring in the complex numbers. You have the congruence subgroup property doesn't hold on the nose. There's something called a congruence kernel, which means that not every quotient is of the form GLN.
Are you saying it's easier like for quadratic imaginaries or something where you have only one embedding?
So no, you have 2 embeddings for quadratic imaginaries. You have the
oh yeah, 2. Okay.
Yeah, so you always have more than one embedding if you're not Z. And then infinite unit groups are something weird that we don't see for Z or for quadratic extensions, or imaginary quadratic extensions. Infinite unit groups are going to be an issue because the unit group, of course, controls the index of SLN and GLN. So when you're working over Z, you can play pretty fast and loose between whether something is an SLN representation or a GLN representation, because it's just index 2. But when you're infinite index, that's a bigger problem. And then finally, how do you tell that a vector space is finite dimensional? This is like a funny question. But I mean, so one thing that kind of annoyed me, annoyed me about Peter's work, and then also annoyed me about my work, is that we have these conditions that seem sort of external. These, like, we were imposing these pointwise finite generation, or sorry, pointwise finite dimensional or pointwise rational conditions. But why should those things hold, or how do we kind of force that situation? So these are kind of the things that were bugging me. And so I'd like to kind of tell you a bit about my now understanding of these issues, as well as sort of there's one other thing that I didn't think of at the time, but has sort of come up in the meantime.
Wait, Nate, I have other things that should have bugged you. No.
Tell me at the end.
Okay, it's just other algebraic groups other than SLN, right?
Yeah, no, there's that's another whole nother story. But all right, let me keep going. So
I did the symplectic groups at least.
Yeah, the symplectic groups we should expect.
That's true. That's true. Sorry.
So, all right. So let me talk a bit about these issues. So, all right. So first, I want to talk about now if I have a general finite ring, and I should say finite commutative ring. So as Jordan mentioned, we don't even know the representation theory for a single GLN R if R is Z mod P to the M for some M larger. So like the hope of like some nice combinatorial labeling kind of goes down the drain. We don't even have such a labeling for a single one. But nevertheless, what I can show now is that if I have a finitely generated VIC module for a finite ring R, then there is a stable labeling. There's a stable way of labeling these representations so that the multiplicities stabilize. But now instead of some combinatorial set, instead of like the collection of all partitions, we just take all irreducible representations of GLDR for all D. So I don't know how to label that, but I do know if we collectively take all of them, that gives us a stable labeling for.
So let me understand here, Nate, are you saying, I think if I understand correctly, you're saying you start with some irredeemable mess, which is the character theory of these groups, but there's some operation which corresponds to adding a box to the top row, and that you can define even if you don't have names for the characters.
That's exactly what's going on. So,
I mean, it's not so different from the situation that we're in with, FI modules and characteristic P, where like you don't have names for the mod P representations of Sn either, but you still have some notion of what it means to go up.
I have names for the mod P representations.
Okay, I don't.
but yeah, so it's not so different. So we still have it. So I can't see the chat. So if someone has a question, you can interrupt me, but I can see that someone is typing things. All right, but we have some stability thing, and what I can say is, so the proof I have is not a great proof, but it works, and so it relies on these Deligne categories, or rather Knopp's version of Deligne categories that are for these finite linear groups, where basically he proves a very similar result there, and then the proof of mine is just showing that these things are compatible with each other, which is harder for VIC than it was for FI, but fine. So it's not a satisfying resolution necessarily, but at least like we know what the picture is now. Unfortunately, also these methods don't give bounds on when stability happens. So I know there's some generic answer, but probably if you're generated in degree D, you get stability at like degree 2D, but I don't know. It's like there's a constructability thing in the middle of the argument. And again, I just want to highlight that like I don't actually have any sort of combinatorial hold on this indexing set. It's just the collection of all irreducible representations of these different groups. But oh well. All right, so let me move on to the next thing. So now suppose I have two rings, R1 and R2. So instead of looking at just VIC, I can take a product, take VIC cross VIC, but for these different rings, and I can consider modules over this. So these look now like a grid. So instead of being a sequence of representations, I get one for every pair of natural numbers. And it's the property that Vij is a representation of GLI of the first ring times GLJ of the second ring. And you might say, okay, why would I do this? The observation is that the diagonal terms are a VIC R1 cross R2 module. So I'm sort of taking VIC R1, R2, and I'm just sitting it inside this larger sort of two-dimensional thing. And so how does this help us? Well, I mean, it helps us in the fact that we now have more directions to go. And so now let me go to the case where R1 and R2 are finite. And so what ends up happening, so first of all, we have Noetherianity, kind of the same finite generation descends to sub-objects. But we also have that finite generation descends to restriction to the diagonal. So if I have a finitely generated module for this product of VIC categories, it's still finitely generated on this diagonal. And moreover, here's the most bizarre part. Everything arises this way. Every VIC R1 cross R2 module can be extended beyond the diagonal to something finitely generated, which is bizarre, but ultimately not that kind of surprising, because it turns out that the analog of free modules are just kind of products of free modules in the two factors. And in particular, a free VIC R1 cross R2 module is the restriction of a free VIC R1 cross VIC R2 module. And then once you kind of have that, you take a finite presentation and it kind of follows formally. So that it's a weird thing that ends up happening, but it's useful. And the reason I wanted this is that it lets us decouple. So if I have a finally generated VIC R1 cross R2 module in characteristic 0, then again I can take some filtration of it where the successive quotients are now tensor products of something in the first factor times something in the second factor. So in particular, this lets me decouple the primes for when I had these VIC Z modules and I had a part that was coming from a finite quotient. I can now separate, something coming from a power of 2 and something from a power of 3 and something from a power of 5. So this gives me this sort of adelic tensor product decomposition over the integers, which is really what I wanted. All right, so that's that story. So all right, now let me say a bit about what happens for GLNO, trying to kind of generalize the integer case. So now instead of just having Z sit inside, my algebraically closed field, there are a bunch of ways to do it. So there's sort of a Galois group's worth of embeddings of a number field into its algebraic closure. And so I'm going to say that a representation of either GLN or of SLN is good if it's a direct sum of kind of this answer that we had for Z, right? So I'm going to take G different algebraic representations, and I'm going to restrict them to O along these different embeddings. So I have kind of G different algebraic terms, and then a finite term that I'm going to impose factors through a finite quotient of the form GLN O mod A. So these are not all finite quotients necessarily because of this sort of congruence kernel issue, but it's a lot of them. And so I'm going to say that this is a good representation. These are the nice ones. All right. And all other representations are bad. And really what I want to say is like good and bad are sort of going to be conditions on like the irreducible or indecomposable components, and kind of think of it that way. Also, all the other ones.
Can I ask a question?
Yeah.
To what extent is this similar or different to a representation of the restriction of scalars of GLN to Z?
Let me. I don't know. I would have to think about that.
Okay. Okay.
Well, we might see something related on there. But okay, so all our representations are bad. So for SLN, this notion of bad is really just coming from this congruence kernel. So you potentially have this extra kind of cyclic central extension that arises in the profinite completion of SLNO. And that can act, but it'll act by a scalar. I mean, it's a central cyclic thing, so that's not so bad. For GLN, here's where this infinite unit group can throw a wrench in things. So you now have this extra center, which is itself like just a finitely generated abelian group, and that has all sorts of weird representations, right? Including things that are not coming from GLN, the algebraic thing, or factoring through a finite quotient. So we have non-algebraic, non-finite ones, and they're not semi-simple. They're extensions. So that's bad. But all right. So now let me say a bit about finitely generated pointwise finite-dimensional VIC modules. So first of all, we get an theory. This is in characteristic 0. Well, I don't need algebra to close for this part. So Noetherian entity, great. All these things that I was just warning you about don't happen once you're far enough along. So this is actually kind of the beautiful thing. So there's all these things I was worried about in proving a version of the super rigidity for other rings of integers. And they're just not compatible with the VIC structure. So it's you have this kind of nesting of your representations in a VIC module, and they just don't behave well with either with these sort of congruence kernels or with these weird actions of the center. So while for any like particular n, you can have kind of weird stuff happening, the fact that we have this nesting rules these out past some point. So all the badness kind of is torsion basically. And so once you have that, then you can hope for something like this, that we should expect to have a finite filtration where successive quotients are a tensor product. Now we have sort of G different algebraic terms corresponding to the G different embeddings of our ring into the algebraically closed field, and then again a finite term, which again by the previous theorem we could further break up the finite term according to primes, but it's sort of easier to just break it up here. So this is what to expect, and I have this as a conjecture. It's mostly proved. Sort of at this point, I have the overall proof is set. There are like there are a lot of technical things that need to prove, and the problem is that like often it'll be something is in the literature for, for PIDs or something. And so I need a version that works for Dedekind domains. And so there are a lot of technical kind of issues that I still need to like address, but morally, this is something that I know how to prove. Like, so I'm listing it as a conjecture because it's not 100%, but it's close. So this is what to expect. Like the theory entity and asymptotic goodness are 100%. Like, perfect. Okay, so I want to get to the final thing. So I'll go through this pretty quickly. So another thing that is not one of the issues that I was having that I mentioned earlier, but it sort of showed up along the way, is that I can also compare VIC modules over different rings. And in particular, I can compare VIC modules for a ring R and VIC modules for an algebra over R. And I'm going to assume that algebra is like a unital algebra. It's free. I want it to be free as an R module and a finite ring. And then the conjecture is that if I restrict a VIC module over the algebra to a VIC module over the ring, then that should preserve finite, generation in finite degree, but multiply the degree of generation by at most this rank.
Nate, is that inclusion drawn the opposite way? VICR, if I have a VICA module, I can sort of forget about A and just think of it as I just want to make sure you say R is included in A.
So R is included in A gives me a restriction map from VIC modules to the other direction. Yeah, so this is an inclusion of the category VIC, but the functor on.
Oh, I understand. Now I got it. Yeah. It's the category, not the category of modules.
Exactly.
I got it.
So the conjecture is that this preserves finite generation and multiplies this degree by M, by this rank of A as a module over R. And I can show this over a finite field. So like, this is not an unreasonable thing to assume. I get a worst degree bound. But I think this is the right answer because for dimension growth reasons, if I do this restriction, it really looks like something that's generated in degree M times D. So that seems to be the right answer. And it looks like it holds, now that I have kind of these two super rigidity statements, it also looks like it holds for kind of pointwise VIC-Z modules and pointwise VIC-O modules. But I mean, kind of the problem with these things is always that I don't have things like the pointwise finite generation means, or the pointwise finite dimensionality means you can't work with like free modules. So it makes things harder. So I kind of don't know how to approach this for these rings yet. But one thing that's cool is that even for the finite fields, this means that there's some sort of stability that happens for restricting from GLNFQ to the K to GLNFQ. And as far as I can tell, this is not something that has been noticed before. So like, even just kind of coming out of this, we're seeing kind of new stability results that maybe we're not seeing previously. All right, I know I kind of rushed it, but I want to get to this last part because I think it's cool. And so I want to talk about finite dimensionality and sort of detecting finite dimensionality of representations. And so I'm going to prove a lemma that has nothing to do with stability, but I think it actually might be kind of an independent use for some of you. And then I'm going to, well, I'll at least state an implication of this lemma for representation stability. But so let me set it up. So suppose I have a group and a representation of the group. I say that a vector is G finite if it generates a finite dimensional subrepresentation. Right, so the span of all of it, the span of its orbit is finite dimensional. And then I'll say the representation itself is locally finite if every vector has this property. Right, so a locally finite representation is, you can think of it as sort of just like a union of its finite dimensional subspaces. All right, and so just a stupid observation is that if you have local finiteness and you're finitely generated over the group algebra, then you're finite dimensional. So it's sort of halfway towards finite dimensionality. All right, but here's the lemma. Lemma is that a representation of SLN-O is locally SLN finite if and only if it's locally SL2 finite for the standard copy of SL2 inside SLN. And this is surprising. Like, this is not something that should happen for infinite index subgroups. So for example, if I just take a free product and I take one of the factors to be finite, then any representation of that free product will be locally finite for the first factor. But
Sorry, Nate, did you say for which embedding of SL2L?
the standard,
SLN,
the one sitting in the upper left corner.
Oh, that?
That.
Okay, because I was going to, if
Yeah,
you
no,
had
it's
one
not-
that's like sort of Zariski dance or something,
Nope.
then it would
No,
be
it's
more
the
believable.
The stupid one, or the obvious one. I'm gonna prove this lemma for you guys because I think it's really cool. So let me give the proof. So okay, so let me have some notation. So EIJ will be an elementary matrix with a single entry A, kind of in position IJ, and then ones on diagonal and then zeros everywhere else. So here's a theorem, not due to me. So this theorem is due to Carter and Keller. This is called bounded elementary generation. So it says that I have some sequence of indices. There exists some sequence of indices, importantly not depending on my group element, such that every group element can be written as a product of elementary matrices kind of in that sequence of, in that fixed sequence, where now all that we can vary are what the entries are. So as G changes, these AIs are changing, but the indices are not.
So this depends on the small n?
This depends on the small n. So this is for a single n. This is a non-stable statement. But yeah, this is true for every n bigger than 2, I should say. This is not.
And can they repeat, or is it like a sequence of distinct?
They can and have to repeat. If I were doing this over a field, you could do it without repetition, but for over something integral, you have to repeat. So it's some
The
word.
capital N could be like really large compared to little n as the notation.
It's not that large. They can bound it like I think quadratically in the middle.
Oh, okay.
No, well, the original thing for SL3 was 57, but
Yeah.
then it's gone down a lot for SL3Z, but
Yeah, it's
gone down a lot.
been improved. All right, so now let me prove the lemma for you. So each one of these elementary subgroups is conjugate to the one that's in our copy of SL2. So if that copy of SL2 acts locally finitely, any conjugate copy of it also does. And then we just take our vector and hit it one by one with this sequence. And at each step, we start with something finite dimensional, and we have this local finite dimensionality condition. So each step preserves finite dimensionality. And so by the time we get to this entire thing of length capital N, we have it stays finite dimensional. So that's the entire proof of that lemma. Cool. So I hope that might be useful. So I'm out of time, so let me just briefly go through my last slide. So the punchline of all that, why I got interested in that finite dimensionality statement is the following. So if I have a VIC module that's generated in degree D now has to be at least 2. If it's finite dimensional in degree D plus 4, then it's finite dimensional forever. And that 4 can be improved to 2 if you're a PID. So you get a slightly better bound if you're a PID versus not a PID. And the proof goes that this local SL2 finiteness condition is something that plays well with the VIC structure. So we can kind of propagate this local finite dimensionality condition via representation stability. And then this lemma implies that local finite dimensionality for SL2 implies kind of global finite dimensionality everywhere. So that's the kind of proof in a nutshell. And this bound of 4, 2 comes from degrees of generation for shifts of your module. So as a corollary, I can show that if the second homology of a Torelli subgroup for odd Fn is finite dimensional for any value of n at least 8, then it's finite dimensional everywhere afterwards. So yeah, that's it. Thanks, guys.
All right, questions?
So I have a question, Nate. Since you mentioned that in several places you have sort of like technicalities that come upon you when you want to sort of, because something's not a PID and you're like, it should still be fine for an arbitrary Dedekind domain, but there's some issue. Is there a version of this story where you say locally free instead of free everywhere and sort of study locally free modules with it? I mean, that's in number theory, that's sort of like usually what we do if something appears to be hard because something's not a PID. We realize we meant to say locally free when we said free and then everything is okay.
So it definitely like kind of, I don't know, I haven't defined, but it's sort of, it seems to come in like in these arguments. I mean, you end up with something that like, you know, you want it to be a free submodule, but actually, you know, it's like a free submodule plus a fractional ideal, and that screws up your bound somehow. But like that morally, like you're right, like it, it maybe shouldn't matter that much. Yeah, I don't know if there's like a nice a sort of a nice clean way to set this up better for Dedekind domains. Yeah, I mean, I will say it's kind of interesting how it comes in sometimes. So like, even in this last thing, I have these different bounds for a PID versus not a PID. And it comes from asking about degree of generation for a shift. And it turns out that like, you know, I can prove a sort of degree bound for generation when it's a PID, and it actually uses the Smith normal form. And it's like, you know, the Smith normal form is some factorization that's sort of happening inside VIC, the category itself, and then it manifests itself in VIC modules. And then of course, you know, you don't have a version of that for Dedekind domains, but you can kind of do something almost as good. And it's almost as good in that like, you end up kind of having to boost your rank by at most 1, and it like makes your shifting one degree further on. But like, yeah, I mean, it's kind of, it was kind of interesting seeing how these sort of PID conditions or the sort of Dedekind domain properties were kind of manifesting inside VIC. But yeah, to your point, I don't know if there's a better way to just set this up so that it works kind of on the nose for Dedekind domains, but it wouldn't surprise me.
Okay, so since we're past 2, I think we should officially wrap up. So let's thank Nate again, and I'm going to stop recording, and we can stick around and talk more.